What is associativity? For all A, B, C in S, A dot B dot C is equal to A dot B dot C. Okay. So I may not write that quantification every time. Then another possible property is existence of an identity element. Okay, or simply existence of identity. So there exists, this is important, there exists an element, say E in S, such that A dot E is equal to E dot A is equal to A for all the elements A of S. The existence of inverses for all A in S, there exists Y in S, such that A dot, well, use consistent notation, there exists B in S, so that A dot B is equal to B dot A is equal to E, where E is the identity element defined in the previous axiom. So for this to make sense, this axiom is required, or this property is required. Okay, I'm defining properties independently. I'm not saying S has these, just saying these are possible properties. But of course, for this to be defined, you need this second one. Okay, not the first one necessarily. Okay. Even if the operation is not associative, you can define identity and inverse. Okay, fourth one, again a possible property only. Commutativity, that is for all A B in S, A dot B is equal to B dot A. Okay, now these are possible properties or possible axioms that our mathematical structure which we define may satisfy. Okay, by the way, if it is just this much, right? I think this is not in the notes. If it's just this much without any properties, then this is called a magma. Okay, I think in an older terminology it's called a groupoid, but nowadays groupoid means something else. But it's called magma. Okay, just a set with a binary operation on it. Whereas if you have satisfying property 1, okay, then this is a just set together with an associative binary operation is a semi group. Then so satisfying 1 and 2, that is a monoid. So a semi group in which an identity element exists. Okay, that is a monoid, and if it satisfies all of the first 3 axioms, then we have what is called a group, okay, which is our main objective study here, but we'll sometimes refer to monoid and semi group also. And if it satisfies 1, 2, 3 and 4, then it is an abelian group or commutative group. Okay, in general you can say any of these satisfying 4 in addition is a commutative semi group or commutative monoid or commutative group. Commutative group specifically is called abelian group. Other things we don't say abelian monoid or abelian semi group. Commutative group is generally called abelian group. Okay, so that's for the definition. You already know this. Let's look at a different point of view for this. Okay, which may lead later to some category theoretic definitions. Okay, so in category theory, the basic idea is that your objects of study are not necessarily sets. Okay, when you have a set, all of the abstract algebra that we study, we start with the set. together with some operation or something. Okay. If you are studying lattice theory, you start with set together with a partial order relation, or if you're studying graph theory, you start with a set and another set of particular subsets of it. So vertex set and edge set. So these are all structures, mathematical structures, which are basically defined using sets. Of course, in analysis, you have metric spaces, topological spaces, which are again sets with some functions, or or a collection of sets with some properties and so on. Okay. But in category theory, we try to do away with the notion of starting with a set. We consider an object as an abstract thing which we cannot look inside to see the elements of. Okay. So what we have in category theory are some objects which are just axiomatically defined, and morphisms also axiomatically defined. So morphisms you can think of as functions, but they may not be functions. They behave like functions, but they are again defined axiomatically. Okay, we'll come to that in category theory. So right now, in an attempt to move towards that direction, what we'll do is we'll start with sets and functions and define groups using sets and functions rather than using elements. Okay. But then you see that this definition can be generalized to categories because it does not refer to elements. So how will we do that? By the way, if you studied universal algebra, then also this is familiar to you. Okay. So let's say G is a set. Okay. Then you have three functions. G set G together with three functions M, E, and iota, which I'll just call I, where M is basically a binary function, a binary relation. E is so what is this? So by this dot, I will denote any singleton set. Okay. So you can just take set with 0 or 1 or whatever, but the object, the element of the set doesn't matter. So we just denote it by dot. In fact, you can write the set itself as dot. Yes, please come in. You can denote the set itself with the element itself with dot, but anyway, to avoid confusion, I will not do that. And iota is a function from G to G. Okay. That's okay. This does not make it a group. But now I say that such that following diagrams commute. Okay, if you don't know what that means, I'll tell you. This is the function M cross ID. I'll say what that means. ID is the identity function. This is ID cross M. Again, ID is the identity function on G. Okay, ID on the set G. Okay, not the identity element, the identity function on G. So what is? I mean, this is defined in any set, right? Anyway, just for sake of completeness, I give the definition. So what does it mean when some more diagrams are there, but what does it mean when I say that this commutes, and what is M cross ID? So M cross ID, if you have two functions like this, f is a function from A to B, and let's say G is a function from C to D, then f cross G is a function from A cross C to B cross D. Okay, how do we define it? A comma C in this, gets mapped to, we want an element, so B cross D. A cross, I hope I don't have to review. What is Cartesian product of two sets? Set of all ordered pairs with the first element from the first set, second element from the second set. So these are Cartesian products of sets, just sets, okay. So the elements of A cross C are ordered pairs A comma C, where A is from A, C is from C. And elements of B cross D are ordered pairs, B from small b from B, small d from capital D, right? So we need to map AC to something here. What can it be? F of A and G of A. That's the only choice, and that is the, so that is naturally defined. Okay, we don't have to assume anything about the sets A and C in order to define this. We don't need to know what the elements are. This can be defined in general. Sorry that that's not very clearly written. So that is that's always defined. So in this case, what is M cross IDG? Here you have Cartesian product of three sets, correct? G cross G cross G. So what is M cross IDG? M is what? What is the signature of M? G cross G to G. So when you consider this, you can take this as a set. So M is a function from G cross G to G. Okay. On the other hand, ID is a function from G to G. So this makes sense according to the definition, right? So basically this sense so if you take an element X, Y, Z here it gets into what? Ordered pair M of XY comma just Z, correct? Right? This gets mapped to this. Followed? Similarly, what will this do? How will this mapping go? Here you have to consider G as a set on which IDG is acting, okay, or IDG is defined, and this second G cross G as a set on which M is defined. So that again, if you take the same element X, Y, Z, here it goes to X comma M of Y, Z. Right. Now here there is nothing to do. So just apply M. So you get M of XY comma Z. When you go from this to this, when you go this way, you get M of X comma M of Y comma Z. Okay. So what does it mean to say that a diagram commutes? So suppose you have suppose you have a diagram like this where A, B, X1, etc., Y1, etc. are sets. Okay, this may be M also, not the same number. So here you have some functions like F1, F2, etc., Fm, G1, G2, etc., Gn, so on. Okay. So what does it mean to say that this diagram commutes? Okay, this commutes if, see, when you have functions like this, you can compose them, correct? How do you compose two functions? I mean, in what order do you compose two functions? If you have F and G like this, what is the composition of F and G? G after F, okay? G circle F or G of F, whatever you want to call it. G of F, G of F, G circle F, G after F. I'll say G after F, so you always remember the order. Okay, so here you will get Fm after Fm minus 1 etc. after F1. Okay. And on this is another way to go from A to B. Another way to go from A to B, that is Gn after etc. G1. So the meaning of saying that the diagram commutes is saying that these two compositions are equal. In general, they may not be correct. If you just write some arbitrary functions here, just because the domain and codomain are the same, that doesn't mean the functions are the same or the compositions are the same. So by saying that this commutes, we are saying that there is some additional restriction. The functions are such that they commute. Okay. Is it fine? I don't know if it's visible to you. Okay. So here, when we say that this diagram commutes, ultimately what does that mean in terms of elements? That M after M cross ID must be equal to M after ID cross M. But in terms of elements, that means that when you take an arbitrary element here and apply this composition to this, what we get is exactly this M of xy comma z. And when you apply this composition M after ID cross M to the same element, what you get is M of x comma M of yz. Correct. So this commutes means that these two, means that these two are equal. Okay. To say that the diagram commutes means these two are equal. How does that relate to the definition of a group? This is associativity. M is of course a binary operation on G. So when you say this, you're saying exactly that if you write M as dot with the infix notation between the elements rather than before the elements, so then you are saying exactly that this one, that is x dot y dot z, must be equal to this other thing which is x dot y dot z. Okay. So notice that we're defining it more or less in an element free manner, only using functions. Okay, of course functions are defined in terms of elements, but that's a different thing. So if you have an axiomatic notion of objects and morphisms, as we'll see in category theory, then this will still work because you don't have to explicitly refer to elements in this definition. Okay, so this is so far associativity. Now we have to look at the other axioms as well. So we'll come to that. Again, this is given in the notes. You can just read that as also. Select and resist. Okay. So next diagram. Oh, right. This is not. Right. So if you do G cross G2, by the way, if you have A cross B, then you have two natural so-called projections from A cross B to A and B. What are these? Phi1 maps AB. So if you take A comma B here, Phi1 maps AB to A and Phi2 maps AB to B. Okay. Again, these are naturally defined whenever you have Cartesian product. So here what I'll do is, right. Again, I take G cross G cross G. I think I made a mistake here. Oh, right. Yeah, I got it. I have to write it as two different diagrams. There's no way to combine it into one. So I'll redo this. So one is singleton set cross G. Okay. Right. Okay. So consider singleton set cross G and the map pi2 from that to G. Okay, pi2 will go from singleton cross G to G, whereas E cross ID, E is a map from singleton set to G. Forget identity element right now, just think of it as a map. So E is a mapping from singleton set to G, and IDG is map from G to G. So E cross IDG is defined as before from singleton cross G to G cross G. Okay, once I get there, I can apply M, correct. So again, if I say that this commutes, what does it mean in terms of elements? First of all, what does this map do? What is the domain here? A singleton set. So this is as good as what? Any map from a singleton set to a set is as good as what? An element of that codomain, right? It is, you can call it a function, but really it is just able to map to one element because the domain has only one element. However many elements you have in the domain, you cannot map to more than that elements in the codomain, correct? So if you have only one element, if you have exactly one element in the domain, then essentially what this does is E of that small dot, I'll say, is the element of this, is some element of G. That's all that matters. If I know what this is, then I know what this function is, and if I know what the function is, I know what this element is. So the function is as good as the element. Okay. Other functions are not like this. If I just tell you the image of a function, can you tell me what the original function is? Not in general, but in this case you can. If you know that the domain is singleton set, then knowing the image is equivalent to knowing the function itself. Okay. So here what happens? You take an element here, which is say dot, of course, comma some x. Okay. So along this function, it goes to what? E of dot, which is the only element in the image, comma x, because that's identity function. Whereas along this one, it goes to what? Just x, right? Because the projection onto the second component of the product, so it is just x. So now this way, this goes to G as what? M of E dot comma x, or in operation binary operation notation, it is E of that dot x. Okay. So what does it mean to say this commutes? This must be equal to x, or we are saying that this E of this, let's write the product as star for now to avoid confusion with this dot, should be equal to x. Okay. So essentially the existence of this map together with the commutativity of this diagram tells you that there is some special element of G, namely the unique element in the image. There is some special element of the set G such that whatever x you take in G, that element star x is equal to x. This defines what? Identity or left identity specifically, right? And so the other diagram that you can make in a similar manner will have G cross dot phi 1 to G IDG cross E. Okay. So this should commute as well. So these two should commute. That would give you, so from the commutativity of this, you would obviously get x star this special element is also equal to x. It's the same element. Okay. X is arbitrary. So the commutativity of these two diagrams gives you existence of identity element. Okay. So far with these three diagrams, what we have is a monoid. Right. Now for the third one, I. So obviously I'm going to use this to define the inverse. So how to define this? You got all this, right? I'll erase it. Make space for the next diagram. Okay. Is that signature correct? If I do I cross IDG, that takes me from G cross G to G cross G, because both I and identity function are maps from G to G, correct? So that works. And what is the other one I can do? Similarly, IDG cross I, right? Okay, and then obviously, what is that going to be? M. Now this should commute. What does that mean? No, not just this much. Okay, I'll add one more. Right. What? Okay. Yeah, this should commute. I'm not mentioning what that map is. I'll tell you why. This should commute. What does it mean though? If you go, so for such a diagram to commute, so earlier I showed a diagram where you had just two parallel paths, but generally you say that a diagram commutes that in a big diagram, whenever you have any two parallel paths, that part commutes. Okay, so here can you find parallel paths? Parallel paths means some sequence of functions which starts with one set and ends with another set. So domain and codomain are ultimately the same for the compositions. So here, this is one path from G cross G to G. This is another path from G cross G to G. One more path is there from the same G cross G to this, not from this. From the same G cross G to this, one more is there, that is the middle one, right? So this commutes means this part commutes and this part also commutes. Okay. But what is this? What is this function, first of all? G cross G2 singleton set. What can that function be? Do I need to define it? Do I need to define what function is there from G cross G2 singleton set? No, because there is only one, right? If you take any non-empty set, or any set, and you take singleton set, then there is always one and only one function from the whatever given set to the singleton set. You have to map all the elements of that set to the unique element of the singleton set. There is no choice there. So this, I don't need to specify what that map is. There is only one possible map. But once you do that and then map to G, what happens? Ultimately, it doesn't matter. If you start with any element here, so I'll write. If you start with an arbitrary element xy, here. Here it goes to the unique elements a dot of that. It doesn't matter. Okay. But after that, whatever this function is, after that, what happens? You get E of dot. Doesn't matter what you start with. Okay. In fact, this can be any other set also. Ultimately, if you compose E after any other function, the result will be E of dot. Okay. Only the domain will be different, but the image will always be the same. Okay. Okay. So that takes care of that. Now, if you go this way, for example, what do you get? This way, if you go, this is ID and this is iota, which I don't know what it does, but I'll just write this. Right. And so now when you do this, what do you get? This maps to M of x comma I of y. Similarly, on the other side, what do you get? M of I of x comma y. Now, to say that this diagram commutes means these two compositions, this composition and this composition must be equal, which means these two must be equal. This composition must be equal, which means these two must be equal. So what does it give you? Corresponding to every element x, there is a specific element I of x, such that when you apply the binary operation with, oh right, I'm sorry, I did make a mistake here. That's what I. This should be just G. Okay, it is not G cross G. My mistake. It is just G. So I'll modify this also. I'm so sorry about that. I'll tell you what this function is. Yeah, sorry, not y. You need x and I of x only, right? Not some arbitrary I of y. That would be completely different. Okay, so right, what does this do? This is different from. Okay, these are not the same thing. IDG comma I means ID. So if you have F from A to B and G from C to D, then F cross G is from A cross B to C cross D. Whereas suppose you have only as a domain, you have just one set and you have two functions from that set to some other set. For example, if you have F from A to B and also F from A, also G from A to C from the same set to 2. Then f comma g, not f cross g, is a function from A to B cross C. How is this possible? You take one element of A, you can map it to two different elements. One is f of A, one is g of A. F of A is an element of B, g of A is an element of C. So that's it. So it maps to f of A comma g of A. Okay, using the same element A, you get two different elements, one in B, one in C. So this is that mapping. Not to be confused with this mapping. Okay, right. So you take one element of G, namely X, map it using this to X comma Ix, using this to Ix comma X, and once you apply the multiplication or the operation, you get Ix dot X on this side and X dot Ix on this side, and along this direction you get that special element E of dot. Now to say that this commutes means that these three should be equal, which means that I of X should be what we call the inverse of X. Okay. So from the these four diagrams, one more was that, from the four diagrams, we can define a group without referring to elements really. Okay. The fact that these are functions and functions are defined in terms of elements, that is secondary. Okay. You can do this if you have some abstract notion of functions which does not use elements. Okay, that we'll see in category theory. Okay, so that we'll come back to such things later. Now we'll go ahead with basics of group theory. So what are some basic properties of groups, which you already know? Identity element is unique. Inverse of any element in a group is unique. Okay, I mean it exists and is unique. Identity element exists in a group and unique. I'm not going to prove those. You know the proofs. Okay, very simple proofs are there. So, but some basic questions. You define semi-group, group, monoid. Can an empty set be any of these things? Because you should ask once you have the definition, what are the possible sets that can form these structures? Can an empty set, does an empty set satisfy any of these properties? Which is that? Only property one you mean? Yes. So a semi-group can be empty. Okay, maybe some textbooks may define non-empty, but actually it can be empty also. So the empty set is together with the empty function. When you have empty set, you always have empty function from that to any other set. Okay, which maps nothing to nothing. That's also a function. Okay, only if you have elements you are required to map them. So semi-group can be empty. Okay, and anything else also. Whereas these cannot be empty. Why? It is not that we define them to be non-empty. Why? Yes. Yeah. Axiom 2 says there exists an element satisfying whatever property doesn't matter. There exists an element. As soon as you say there exists, it is non-empty. So you don't have to define it as non-empty, but okay, these cannot be empty by the second axiom. Okay. So that's just one thing to keep in mind. So the smallest possible group or monoid can be what? Singleton. With operation, of course, there is only one choice of operation again to define on it. So if you take a set, singleton set, let's call it E, I mean the element E, then you have to define E dot E is equal to E because there is no other choice. There is another point I want to mention. Did I leave out any axiom? Closure? Is it required? Binary operation tells you that it's closed. I don't have to separately mention that it's closed under the operation. If I've written this as a binary operation on that set, not S cross S to some other set, right? Some larger set is S cross S to S. So by that type signature of the function itself, it is closed under the operation. You don't have to separately mention. Of course, you may, when you take some operation defined from some familiar operations, you may need to remember to check that it is indeed a binary operation. So that's why we usually mention closure. Okay. Fine. Now, because of associativity, what we can do is, if you have some finitely many elements of a group G, then this expression is well defined without any brackets. Okay, I don't need to put brackets. Associativity tells you that no matter how you bracket this, not changing the order of terms, changing the order of bracketing, okay, that doesn't change. So this is well defined. So we can just write things like this. Okay. Again, there is a formal proof for that by induction, which we won't go into. Now, as a special case of this, if I write x dot etc. x n times, that means all these xi's are equal to one element x. Then we will denote this as x power n for any n. In fact, obviously not real number or something, it's integer, positive integer, right? So I will use this that Blackboard Bold n for set of natural numbers 1, 2, 3, 4, etc., not including 0. Okay. So for any n in them, this is defined. Then how can you define x power minus n? That can also be defined in a group, not in a monoid, in a group. How to define this? Simply define it as x inverse power n. Again, we already noted that every element x has a unique inverse. So that unique inverse we denote by x inverse. Okay. Once you prove the uniqueness, you can use this notation x inverse. So that is a unique inverse of x. So x inverse power n. Okay. There is an exercise that asks you to prove that this is also equal to x power n inverse. Okay. Fine. Finally, we also define x power 0 to be the identity element. That's a definition. You have to define it that way. It does not follow from this. Of course, if you want the notation to be consistent with your usual laws of indices or exponents, then you have to define it this way. That's the point. Okay. So with this definition, you can prove the usual laws of exponents for any integers m and n. You have x power m dot x power n is equal to x power m plus n. X power m whole to the power n is equal to x power mn. And this one being a special case of that because it's true for all integers m and n. Okay. Yeah. Now another thing that I'll need, which you don't usually see, is monoid of subsets of a group. Okay, just a monoid of subsets of G. This may not be done usually, but it's not that unfamiliar also. So suppose you take the power set of G and also the set of all non-empty subsets of G. This is set of all non-empty subsets of G. This is usual power set. Power set is set of all subsets. So if you take A and B are two subsets of G, then I'll define A dot B as element-wise multiplication. By multiplication, I mean the group operation. Okay. So is there any problem in this definition? It's well defined. I'm not saying anything else about this, nothing like subgroup or something. It's just subsets. This is obviously another subset, right? Because A dot B is an element of G. So this is some subset of G as well. So what does it tell you? That this dot, this new dot, is a binary operation on P of G. Okay. If A or B is empty, then what is this? This is also empty because it doesn't start only because or take elements, right? So by that usual conventions, this is equal to phi if and only if A or B is phi. Okay. If and only if, because if you have some element in A and some element of B, you will have to get some element. There is no way elements can annihilate each other. and vanish, right? So you will get some element, right? So this is empty if and only this. So even if you take this part, dot is a binary operation on this as well, correct? But what structure does this have? So it is a magma for sure. Okay, whether you take P of G or P star of G together with this dot, it is definitely a magma. It is just set with a binary operation. But what else can you say about it? Is it associative? Is this operation associative? Yeah, because we define in terms of elements. Generally, when you do that, it will turn out to inherit the properties. So if you do A dot B dot C, there are two ways to evaluate this A dot B dot C. That will give you bracket small a dot b dot c, set of all elements of that form. But that's obviously equal to a dot bracket b dot c, which is a dot bracket big A dot b dot c. So this is associative. Okay, so associativity is there. So it's definitely a semi group, but I've written it's a monoid. It's a monoid, is it? So you have to tell me what is the identity element of this operation. Singleton E, not G. G would be the identity. Actually, G is not identity. G, I'll tell you what G is. So observe that this is equal to A for all subsets A. So identity is also this. So this is definitely a monoid. Now what is G? G is also an element here. What kind of element is it? Is it identity element? Obviously not, because there can only be one identity element, and this is clearly that. What kind of element is G? What is G dot A? It is G, not A. If it was A, then it would be identity, right? G dot A is A, and so is A dot G. Sorry. Yeah, G dot is G itself, right? So it is what is called an absorbing element or a zero, but that is only if A is non-empty. This is only if A is non-empty. So in this one, so P star of G, this G is a zero. Zero means absorbing element. It absorbs whatever you give it. Okay, kind of like the opposite of identity element. Whereas if you take P of G comma dot, this also has a zero. What is that? Empty. Or, oh, sorry, I went to eraser mode for some reason. Right, this is a zero of this set. Okay, so you have to keep in mind what set you're working with. Now, as special cases, if you have say singleton set A dot B, then we'll just write this as A dot B, or in fact from now on I'll drop this dot notation whether it's for the operation of the group or for this one. So we'll just write AB. Okay, and similarly the other one, like I can also write PA when again you have singleton set. Okay, so these are well defined, right? So this is specifically what, tell me? Set of all elements AB for B belonging to capital B. Okay, so we'll obviously cosets of subgroups. So later when we define that, this is already defined from this. Okay, you don't need to specifically define it. Since I can do this with any number of sets, I can also do things like A, B, C. Okay, this is also well defined. Okay. Now, actually, let me see what I would do. Yeah, there are some exercises. We'll take these up in the tutorial. Okay, so we'll explore all of these in more detail. My main idea now is to give cover the definitions. Okay. Yeah. So we'll take a brief look at homomorphisms, isomorphisms before we even look at subgroups. Mm. So suppose you have a function f from G to H. So if you're just working with set theory, then a function has, you can maybe define some properties like injectivity, surjectivity and all that, but otherwise we don't have any restrictions on functions, right? Whereas when you're working with an algebraic structure or any other kind of special mathematical structure, you don't generally consider arbitrary functions. You consider functions which preserve that structure. So in terms of group, or in the case of groups, what does preserve the structure mean? What is the structure of a group? The group operation. So we require that if you take x dot y, I'll just write it as x, that should always be equal to f of x dot f of y in H. This operation happening in H, right? Or in G, right? So this is then called a homomorphism. You know this. Then you have if f is bijective, then it's called bijective homomorphism is called an isomorphism. Okay, but again, my point here is to define this in a little different way. So let me try to define this also using commutative diagrams. What do we mean by group homomorphism? Um, hmm. Sorry, correct. G, this is H cross H. This is H. Thank you. So I claim that if f is a function from G to H such that this commutes, then f is a homomorphism, and vice versa. If f is a homomorphism, then this commutes. Okay. So commutativity of this diagram is equivalent to the statement that f is a homomorphism. Why is it so? How does it work? Where m is again the group operation. Okay, so whenever I'm writing it as a function, I'll write m. That means the multiplication of the group. Again, this is actually mg, and this is mh. Usually we just write m. It's understood what m it is, but to be clear, we'll write that. Okay. So again, why does this work? How does it encode the definition of a group homomorphism? If you take x comma y, f cross f sends it to f of x comma f of y. And then m sends it to the product f of x, f of y. I'm not writing m of that. It's just a product. Okay, in H. Whereas over here, this goes first of all to xy, the product in G, and this sends it to f of xy. These should be equal. That is our condition. So group homomorphism can be defined in terms of commutative diagram in this way. Okay. What does it mean for it to be an isomorphism? When can we say it is an isomorphism? Another diagram is required, not this. Okay, another diagram is required. Obviously, with something else defined, right? So f is an isomorphism if there exists a G, a group homomorphism G from H to capital G, this map, not element, okay, such that I have to define this carefully now. Right, okay. Fine. Such that this diagram commutes. Is that true? It is an isomorphism if and only if there exists a homomorphism G, okay? Oh, homomorphism G from H to G such that this diagram commutes. Yeah. Why is it? Actually, I don't have to say that it's a homomorphism, it will automatically be. But anyway. What does this actually tell you? The commutativity of this diagram. So if you look at this triangle, that commutes means what? This commutes, this is sometimes used as a notation for commutes or tick mark or something. That means this composition is equal to this because those are two parallel paths. G to G, you can go this way or this way. So if you go this way, you get G after F. That should be equal to IDG. Another one, similarly, lower triangle. Yeah, this way if you go, you get F after G, and that must be equal to what? IDH, identity mapping of H, identity function, right? So this tells you what G is. For F, G is an inverse. Okay. Now the nice thing in group is, as I said, I don't have to say that G is a homomorphism. If F has an inverse, then it will be a bijective map, and then the inverse will automatically satisfy the property of homomorphism. But in other structures, it is not true. In general, it is not true. Okay, so if you're doing this in graph, for example, I have to write, of course, not this kind of thing, but this part is same. For in a graph homomorphism also, if I want to define inverse, or in a topological space, for example, if you want to define homomorphism, you can take a continuous map F such that there exists a function G that makes this commute, but that will not make G a continuous function automatically. You have to assume that it's continuous, okay, separately. Whereas in groups or rings and so on, you don't need to assume that it will automatically be a homomorphism. That's a special property of groups, but keep this in mind when you're working with other structures. Sometimes you have to assume that it's a homomorphism in the definition. It won't automatically. Okay, right. So if you have yes, again there are exercises which we'll take up. Okay, basic definitions I'll mention as we require. Okay, fine. We'll go to subgroups. So again, when you have mathematical structures, it is obvious to think about substructures. So if you have a subset H of a group G, then it's a subgroup of G if it is itself a group. Okay, so if G is I'm abusing the notation a bit. If G is a group with operation dot, then such that this is a group, then we say that H is a subgroup of G, and we write it as H less than or equal to G. Okay, is that okay to say that H comma dot is a group? What is dot actually? It is strictly speaking the restriction. I'm again abusing notation here also. It is actually the restriction of the binary operation defined on G to H. So first of all, that should be a binary operation on H. That means H should be closed under the operation. Okay, so this tells you that if you take X and Y in H, then X dot Y should belong to H. Only then this restriction will be actually a binary operation. Okay, so by writing that, I'm saying that it's closed under that. Then another thing is H should have, so once that is, do you need to check associativity? Associativity follows if it associativity with such universally quantified properties, right? They don't have anything. Existential quantifier is not used in the definition of associativity. That means you don't say that there exists an element satisfying so and so. Correct. So if you have a universally quantified property, I mean property defined by only universal quantifiers, if it holds for a set, it will definitely hold for a subset. That is always true. Okay. So associativity you don't need to check separately. But existence of identity you need to check. So what does existence of identity mean? Here also there are some subtle points which I'd like to bring to light. Again, this definition is well known to you, but you need to keep those points in mind. So when you say there exists an identity element in H, what does that mean? There is some element of H, let's say E prime, such that whenever you take, it's very strange. Oh, so there is some element E prime in H, so that if you take X in H, then X dot E prime equal to E prime dot X equal to X. Correct. But what can we say more easily? Rather than this, what can we say? Yes? The identity element of G, I want to be very clear about it, exists in H. This is stronger than saying this, right? Because this is saying some element is there in H satisfying this property. Of course, if this is there in H, then it will definitely satisfy the property because it satisfies the property in the entire group. But is it equivalent to saying this? Is it necessary for this? So if you are working with a monoid, for example, then these are not equivalent. Okay. If you are working in a monoid, even if the monoid contains an identity element and you take a subset, that subset may have a separate identity element. Okay. But in a group, it happens that if you take an element X and X dot Y happens to be X, then by cancellation, again I didn't mention cancellation laws, you know them. By cancellation, you will get Y is equal to E. So this identity element of H cannot be some separate identity element, it has to be that of G only. So very simply I can say EG belongs to H. Similarly, for any X in H, again it cannot have a different inverse inside the subgroup, right? Whatever inverse it has in the group, if it has it in the subgroup, it must be the same. Okay. So again, X inverse must be there in H. These are properties that define the subgroup. There's a simpler subgroup test which you know, which is very useful, especially when you have to quickly check whether something is a subgroup, which is what, instead of all of this, I can check whether, first of all, it should be non-empty. Usually you can check whether identity element belongs to H. That is the easiest thing, but sometimes you can directly check whether it's non-empty. We don't need to know the existence of identity. And separately, if X and Y are in H, then X Y inverse is also in H, or equivalently X inverse Y is also in H, any one. Okay. So this is another way to check whether something is a subgroup. Okay. Fine. Suppose H is a finite subset of G. G itself may be infinite or finite. By the way, I didn't mention order and all that. Order of the group is number of elements in the group, that is cardinality of the set. It may be infinite Otherwise, we call it a finite group, or we call it an infinite group, right? Finite group of order n means the set G has cardinality n. Okay, so suppose G is possibly infinite or finite, whatever, but H is a finite subset. Then I claim that H is a subgroup of G if and only if H square equal to H. What is H square? HH means we defined already AB notation, right? Element wise multiplication. So H square is element wise multiplication of elements of H with itself, not just squares of elements of H. Not that. You take any two arbitrary elements of H, multiply them, all those products will be in H square. So, right, product of H with itself as a set as defined earlier. Okay, so I claim this. Is it true? What does it mean, first of all? What is another way of saying H square equal to H? Okay. It is an idempotent element of that semi-group or monoid that we defined earlier. That's another way. I didn't mean that, but that's correct. That is, in fact, a question in the exercise also asks you to describe what idempotents of that monoid are. So yeah, is this. But what does it mean in terms of our group? Yes. It is closed under the binary operation. This is just saying that H is closed under the binary operation. So I'm claiming that if you have a finite subset of a group, then it is a subgroup if and only if it is closed under the binary operation. Obviously, if it's a subgroup, it is closed under the binary operation. But why is the converse true? Why don't we need to check these things? Existence of identity and inverses. Okay, that's a tutorial problem as well. We'll do that. Okay. We have 1 minute before the break, so I'll just mention subgroup lattices and just very quickly introduce subgroup lattices and stop. This is another way to think about the structure of groups. Okay. So it depends on whether you're already familiar with lattices or not. Anyway, you can understand them through subgroup lattices without the general theory. But in the appendix of the notes, lattices are posets and lattices are defined. So if you need to refer to that, okay. This is all you need to know. You have the collection of subgroups of a group G. Okay, we have a relation on this. That means if you take any two subgroups, maybe one is a subgroup of the other also, because they are all groups by definition of subgroup. Every subgroup is a group. Then if obviously if suppose H and K are two subgroups of G, two subgroups of G. If H is contained in K, then is it true that H is a subgroup of K? Yeah, because again it satisfies the original definition that it's a subset of K is a group by definition of subgroup, and it's contained in K, we are saying, and H is itself a group under the same operation. All the operations are same, basically restrictions, right? So this is the same thing. This is saying the same thing. Okay. So from now onwards, instead of writing subset, I'll write subgroup whenever it is a subgroup. So this has a relation defined on it, not an operation, a relation defined on it. The set of all subgroups, not subsets, okay, not the power set. Set of all subgroups of G has a relation which I denote by less than or equal to, defined on it. And under this relation, it forms what is called a lattice. Okay. So this relation is a partial order relation, which means it is reflexive. So every subgroup is also a subgroup of itself. It is antisymmetric. Suppose H is subgroup of K and K is subgroup of H. That means basically a set, H is contained in K, K is contained in H. That means what? They are the same set. Also, if H is subgroup of K and that is subgroup of L, then H is a subgroup of L. The transitivity. So this relation has these three properties: reflexivity, antisymmetry, okay, and transitivity. So that makes it what is called a partial order relation, and so this is a coset. Okay. But more than that, you know that the intersection of two subgroups is also a subgroup. So if you take H and K as two subgroups, then their intersection is a subgroup with some special property. What is that? Suppose you take any other subgroup of both, then necessarily that will be a subgroup of the intersection. Okay. Similarly, you know that the union of two subgroups is never a subgroup unless one of them is contained in the other. Okay. But still there is, you can consider the smallest subgroup containing the union or containing both H and K. That means the intersection of all subgroups that contain both H and K. Then again this has a similar property. What is that? By this definition itself, if it is the intersection of all subgroups that contain H and K, and if you take any subgroup that contains both H and K, this must of course be contained in that, correct? Because that will be one of the elements in the intersection that you're taking to define this. So intersection of subsets is always contained in that, right? So this defines what is called the greatest lower bound. This is the greatest lower bound of H and K, and this is the least upper bound of H and K in this per set. Okay, so these are already, I mean, these are always defined. So that makes this, in addition to being a per set, what is called a lattice. Okay. So again, the appendix gives a definition of lattice. So we'll stop for now.